Good afternoon, ladies and gentlemen. It is a great pleasure for me that I can introduce Professor Jiří Mikyška from the Faculty of Nuclear Science and Physical Engineering of the Czech Technical University. He works as associate professor there, and he has been involved in various research on various interesting fluid flow problems, both on modeling and numerical simulation concerning multi-phase flows, multi-component flows, and porous media flows, etc. And today he will speak on an alternative model of multi-component diffusion based on a combination of the Maxwell-Stefan theory and continuum mechanics. So we are looking forward to your talk.
Thank you. Thank you very much for introduction and also for inviting me for this seminar, which I'm very proud of. So this is the work which I did together with my former graduate student Jan Franců. This is another Jan Franců than you know probably.
This is another one.
Another one, yeah. So basically, I will talk about diffusion in a multi-component mixture and about the ways to model it. And then I will show some alternative, which I somehow like for some reason I will explain. And you will see that we will get a model which has quite nice properties and quite different from what we would expect. So I think it should be something which would be of your interest. So if we talk about flow and transport in a homogeneous fluids, then usually we describe these flows by either Euler equation or Navier-Stokes equation of continuum mechanics. And in porous medium, flowing porous medium, we usually use Darcy's law for description of the velocity field and continuity equation for the mass balance. Now the question is how to generalize these concepts to mixtures. So if we have a flow of multi-component mixture, then we usually use the concept of overlapping continua, which means that each component of the mixture is present everywhere. So these components are overlapping each other. We define the densities or molar concentrations, which are defined in the whole space. And then we formulate some laws of transport. And what is interesting to see is that depending on the model, there are different models, but depending on the model, some properties are associated with individual components, like for example, the densities or velocities. And some other components are associated with the mixture as a whole. This is the basic of the theory, which, for example, splits the flux into convection and diffusion parts, and diffusion is just related to as a fluctuation with respect to some average velocity, and this average velocity is associated with the mixture as a whole. But we have different options how to choose these categories, and different choices lead to different mixture theories. So I will show some very basic settings. So for example, if we have a flow of n components, these components are indexed by this superscript alpha. Each component has its own density and its own velocity. Then we can introduce the mass average velocity, which is basically the average velocity weighted with the mass fractions of individual components. So if we have this mass average velocity, then we can take this alpha component flux and split it into one part which flows in agreement with this average velocity, and then to do fluctuation with respect to this average velocity. And usually this first term is interpreted as a convection, and this other term is interpreted as the diffusion flux. And from the definition, it's clear that the sum of all diffusion fluxes is equal to 0. And now the question is how to model convection, how to model diffusion, and these processes are modeled very often separately. But So this is the general settings which can be adapted to different situations. So for example, if we have this diffusion and convection in a free space, then basically we have mass balance equation formulated for each component. But the momentum equation is usually formulated for the mixture as a whole using this mass average velocity. And there are some discussions in the literature whether this mass average velocity is the correct averaging procedure or not, because we can have, for example, mole average velocity or volume average velocity, and we can come up with infinitely many others. And what I'm not really sure whether this mass average velocity is somehow different from this other one, that we should somehow prefer it or not. So this is in free space. There is really some discussion in the literature about these velocities, and I don't know, maybe if you are aware of something which I'm missing, I will be glad if you tell me. But in my view, as far as I know, this question whether this velocity, mass average velocity, is somehow preferable over the other ones or not, it's not clear. For example, in Maxwell-Stefan approach to multi-component diffusion in isothermal and isobaric systems, usually we neglect convection. So basically we say this average velocity is 0. So this is very simple model of convection. And then the diffused flux is related to gradients of chemical potentials in some way. I'm not going into details now, but basically this is how we model diffusion in a multi-component mixture. In porous medium, we usually use Darcy's law to model convection, and then generalized Fick's law, or maybe Stefan Maxwell, to model diffusion. And we put it together like this. But here in the literature, I can see many papers, and some of them are using mass average velocity for the convection. Other one in chemical engineering, very frequently they use mole average velocity. Some of them don't even describe what velocity they mean, and it's not even clear whether the Darcy's law, when used for a mixture, whether it represents the mass average velocity or some other velocity. This is by no means clear. So somehow, when I was thinking about these problems, I was thinking the best way would be not to even split it into convection and diffusion, and just to write the system using all forces as we do in classical mechanics. So basically, what I want to present is a theory in which the splitting of the flux to the convecting and diffusing part is not used at all. So basically, I'm going to propose a model in which the momentum balance is performed not for the mixture as a whole, but by component by component individually. But then we have to think about transfer of momentum within one component, and also momentum transfer from one component to the other component. And here I want to use Newtonian model for the viscosity within a component, and the Maxwell-Stefan model for the exchange of momentum between different components. So basically, this is the idea of the model which I'm going to present. So basically, this is the overview of my talk. So I will be describing the theory which will focus on flow of components in multi-component mixture in free space at constant temperature. I will present the basic equation of the model with some specific constitutive relation. Then I will introduce a simplified 1D model, and I will discuss some of these properties. I will just briefly mention a numerical scheme. I could maybe here I could describe this in detail, but I will just briefly mention the scheme. But I will present some computational results which are really interesting. So as I said, I want to have a mixture theory which will have mass balance and momentum balance for each component. So we have n components, and hat means the set of integers not exceeding n, so 1, 2, 3 up to n. So for each component, we formulate the mass balance equation. So each component has its own density and velocity and no sources. And each component has its own momentum. So this is the temporal change of momentum plus the flux of the momentum over the boundaries. This is the divergence of the stress tensor, which is formulated component by component. These are the sources of momentum from the volume forces. And this is the term which is specified here, which will describe the transfer of momentum between different components. So for the stress tensor, I use the classical Newtonian stress tensor with pressure of each component and two viscosities of each component. Yeah, and this is the Cauchy tensor. And now, what is the key? Is how do we describe the exchange of momentum among different components? So basically, this is this term on the right-hand side. So we have here the gradient of partial pressure minus one term which contains the gradients of chemical potential of component alpha. This is the mole rate, so basically this is mole concentration, and this is some constant which will be used as a parameter, and basically this constant says how these gradients of chemical potential, these are like driving force for the mixing, for the diffusion, and now we see the strength of this diffusion. And this other term, this is basically, these two terms are borrowed from the Stefan Maxwell. So this is the basically friction of components alpha with respect to component beta. And basically what it says is that the friction force is proportional to the velocity difference. And this coefficient, the alpha beta, which has the same notation as it is used in Stefan Maxwell, this is just the inverse of the Dirac coefficient. And to close the system, we assume that the temperature is constant and chemical potentials have to be specified as functions of molar concentrations and temperature. Maybe you will think that I'm missing the pressure equation for partial pressures. But actually, this model is suggested in such way that this partial pressure disappears because I have this term gradient of partial pressure here in this term, and here I have this divergence of T, and the first term is minus P alpha I. So when computing this divergence and this gradient, this will cancel out. So basically, if I just take this momentum exchange term and put it here in this right-hand side and use this simplifying assumptions, then I have for each component one mass balance equation of this form, and this is the momentum balance, including this volume forces, and this is the Newtonian stress tensor without this pressure term. And here I have these two terms, which are from Maxwell-Stefan. In comparison, if we used Maxwell-Stefan approach, we would have this system of equations. This would be the same, and instead of momentum balance, we would have just these two terms equal to 0. So basically, this would, in Maxwell-Stefan, we have the assumption that the driving force of the diffusion is the gradient of chemical potential, and it should be equilibrated with this friction term. And then this constant would not be here because it would be part of this d alpha beta. So in Maxwell-Stefan, we have only d alpha beta parameters, and these are interpreted as binary diffusivities, and basically they mix together two phenomena. One is the friction coefficient, and the other one is the driving force of the diffusion. In this model, which I have here, these two terms are splitted. So basically, the diffusion force from the chemical potential gradient can be driven by this K, and this is now really only friction and nothing else. Yeah? So this is some basic difference from classical Maxwell-Stefan model. So yes, this is exactly what is written here. So now let's come to these closure equations. So if we have ideal mixture of ideal gases, then this chemical potential has its this form. So basically, it's just RT log of concentration, maybe normalized with some additive constant. This can be arbitrary constant. And if we want to use some other equation of state, non-ideal, then for example, we use Planck-Robinson equation of states for hydrocarbons. Then this equation of states or chemical potentials can be split into ideal part and the rest of it, which is non-ideal. So we just have this with tilde. We just denote the non-ideal part of the chemical potential. We will use this splitting in the next slide. So I'm going to simplify the model into 1D. So basically, I'm assuming that I have 1D flow with constant cross-section, a uniform flow in 1D with zero viscosity, and the only driving force or outer force would be the gravity. So now let's take a look. These are the mass balance equation in the usual form, and this is the momentum balance after some simplification. So basically, I'm going back here. Basically, now we have this term is gradient of chemical potential, and chemical potential is proportional to logarithm of concentration. So basically, we can take the gradient of logarithm of the potential, so it's 1 over C alpha gradient C alpha. And the trick in 1D is that we can take this term and put it inside this divergence. And on the right hand side, as the source, we have just the non-ideal part of the chemical potential. The ideal part is basically put here. And then we have this gravity, and this is the friction term. And now we can take a look to the structure of the system. So these red terms are these for the components of the vector of conservative variables. These blue terms, which are inside this divergence, they form the flux. So we have the divergence of this flux function. And what remains on the right-hand side is the source term. So basically, I'm going to describe the diffusion by a first-order system of equations, which looks like a system of conservation laws. And I will show that this system, under some simplifying assumption, is hyperbolic rather than parabolic. So this may be surprise for me. But really, if we take a look at these blue terms, which is the flux function, and we compute the Jacobian, so we are assuming ideal gas, and no diffusion, no viscosity. So basically, it's the same thing as if you want to investigate Euler equations rather than Navier-Stokes. So the same logic, but still containing mixing from diffusion. So this is the Jacobian of the flux. You can see that it's very simple matrix with just 3 diagonals, and we can compute its spectrum, and we see that the spectrum is real. So it's really a hyperbolic system with some sort of. When we have non-ideal mixture, then this term on the right-hand side cannot be included into conservative flux function. So this is more complicated. but still the system can be written in the non-conservative form as of this form, and we can compute this A as the Jacobian minus some matrix which is specified here. But unfortunately, in this case, we cannot tell what is the spectrum of this matrix in advance. So I will just keep the discussion with these ideal gases, which is this is very interesting. So we will assume that we investigate flow in a closed 1D tube of finite length, and the only external force is the gravity, and other forces are diffusion from the gradients of chemical potentials, and of course the friction from different components. So basically, in this interval and of space, and this is the time interval, we solve this system of this form with this non-ideal part, and this is the substance. And as the initial condition, we specify the initial densities and initial velocities. And on the boundaries, we assume that there is no flux over the boundaries, so impermeable boundaries. So this is described for each component. And regarding the numerical scheme, I'm not going into the details, but basically we use operator splitting, and we split the problem and solve the problem first, just the transport part, and then the source part. And we use the explicit finite volume scheme for this, for treating this part. And for treating this term, we use mixed hybrid finite element methods with some mass lumping. And this part is solved using implicit Euler. So this is just a brief overview. And if you are interested, we can take a look to this journal computational physics paper. So I'm going to show you some results, and what is interesting, we have in the literature there are data available for mixing of 2 or 3 components. So we wanted to simulate these experiments. So one example is the mixing of argon and neon. So this is argon and neon mixing in a 1D tube at constant temperature. And basically the initial condition is basically that we have one half of the tube is filled with argon, the other part with neon, with different densities, which are constant, so that we have constant pressure. And here we have molar weights and the densities, and these are the coefficients from the Maxwell-Stefan model, and this is the K, which is not available anywhere, but we needed to tune it. So this is our suggestion. This is the common pressure in these 2 parts and no gravity. So in the beginning, the blue one is argon, and in the beginning it was just constant, jumping to 0 here, and neon is the red one, was 0 here, jumping to this value and continuing here. After 7 seconds, you can see how these are the density profiles as profiles in space. This is in after 7 seconds, 10 minutes, and this is 1 hour. So basically, you can see the mixing as you would expect from binary diffusion, but this is described by a hyperbolic system because these are ideal gases. It's the pressure is just 2 bars, so it's low pressure. So basically, it can be modeled as an ideal gas. So you can see that after 1 hour, it's almost equilibrated. So basically, this is what we would expect from the classical diffusion, but now it's modeled using hyperbolic system. And yes, and actually, I don't have this figure here, but we have also some. This is the computation, and then we can take measurements which are performed at 2 places at minus or plus 0.133 meters, so it means somewhere here or there. We can measure these values as a function of time, and these are the measurements which are from the literature. These triangles and the continuous, these lines are the results of our computation. So we can see that our model can really fit the experimental data very well. And now I have another experiment which is even more interesting, and this is the ternary diffusion, and this is the Duncan-Tor experiment. This is a classical experiment in multi-component diffusion, which was proposed to study different phenomena related to more than two-component diffusion. So basically, the experiment consists of two bulbs, which are connected with this tube. And initially, these bulbs contain a mixture of three components: hydrogen, nitrogen, and carbon dioxide. And in the beginning, we have mole fractions of nitrogen 0.5 in both parts, but in the left part, nitrogen is mixed with CO2, and in the right part, nitrogen is mixed with hydrogen. So there is no gradient of, basically no gradient of this nitrogen composition, but there are steep gradients of hydrogen and CO2 in the middle. And at time zero, we just join these bulbs together and see how these three components will mix. If it was just a binary diffusion, then we would expect that there would be no movement of nitrogen because there is no gradient of composition. But we would expect that hydrogen and CO2 would mix together. But there are cross interaction between different components. So once this hydrogen and CO2 start mixing to each other, they will have the effect on N2. So from something which is originally flat, there will be some wave. And this is the effect of ternary diffusion. So this is our simulation. Here we have these densities of different components as a function of position at different times after 0.08 hours. This is after 2 hours. This is after 18 hours. And we can see from the very beginning that CO2 is spreading into hydrogen. Hydrogen is spreading to left a little bit. This is not much clear visible, but we can see that N2, nitrogen, which was flat in the beginning, starts moving because of hydrogen and CO2. And at infinite time, the system obviously tends to the equilibrium position. And again, for this system, this was measured. So at certain points, somewhere here or there, the composition of each component, mole fractions, were measured as a function of time. And we have this data. So again, we have these triangles are the measurements, and the blue and red lines are the results of our computation. So again, this hyperbolic model can model quite well this experimental data. So that's it. So basically, I hope it will not be too short, but I think we will have a good discussion maybe. So we have developed a theory of mixing which doesn't rely on splitting of the flux into convection and diffusion parts separately. Instead, we formulate this momentum balance for each component individually, and viscous friction is modeled using the Newtonian stress tensor, and the friction due to other components is taken into account using Maxwell-Stefan. And the message is that when viscosity is neglected, the diffusion of components in an ideal multi-component mixture is described by a hyperbolic system of conservation laws, which may be interesting. But we have some numerical procedure to compute it, and we can see that the implementation of this scheme shows good agreement with experimental data. So that's it, and yeah, this is the just the grant under which you have finance. And if you are interested in more details, we have published it in Journal of Computational Physics, January 1, 2020. So basically, it's almost the same title as this talk, and that's all. So,